Thanks for giving me the opportunity to present today, and I hope you all had a good lunch break. So yeah, the topic of this talk is on the galaxies, which I think for a substantial fraction of the audience are essentially foreground, or one might even go as far as saying a nuisance in some sense. But yeah, on the radio side of things, we have learned a lot about the star-forming galaxy population, and of course also the interplay between accretion processes and star formation in galaxies, all the way into the epoch of reionization at this point, thanks to the new generation of radio telescopes. And I basically just want to give you a bit of a panoramic overview of what all we know when it comes to characterizing star formation processes across cosmic time in the radio band. So yeah, this is inherently an exercise that uses, for the measurement of the star formation rate, radio continuum data. And so my title slide, if I just remove the title itself, exemplifies this with the spectral energy distribution of a prototypical low redshift galaxy down below. You see a quite steep slope on the left-hand central side. So I hope you can see my mouse pointer. This is the synchrotron emission here. A shallower component, the free emission, a thermal emission component, as opposed to the non-thermal synchrotron. And then, yeah, this ramps over into the far infrared with the dust. So when we trace cosmic star formation processes in the radio, it is mostly through the brighter of the two components, namely the synchrotron emission. And the images I've included on this title slide really show you how we can see these processes in action in nearby galaxies. So top leftish and lower left, the top left shows a very high angular resolution view of the starburst galaxy M82, taken with the E. Merlin in the UK and EVN observations. And what you see here in the zoom in is a specific supernova remnant tracked over of order 20 years, 25, where you see literally the supernova remnant, the shell expanding over time, and is precisely the shocks generated from such supernova events, which accelerate particles in the magnetic field of galaxies, that generate the synchrotron emission. And the free emission, on the other hand, on the right-hand side, very good example of an object we know well from the nighttime sky, a H2 region, where there's lots of ionized particles, and yeah, them accelerating in the electric fields of the other particles generates the free emission. In this case, yeah, a continuum map in free component of the Orion Nebula in the box I've highlighted here. So yeah, free being the thermal component, less bright, and synchrotron really, by virtue of its brightness, the go-to tracer for star formation in many ways. But they both very much have their role to play, as I will show you. So yeah, my talk is going to begin with outlining why it is potentially very worthwhile to work with radio continuum emission as a star formation rate tracer. But of course, there are challenges, which I'll touch upon as well. But we already have exploited this emission mechanism to learn quite a few things about the star-forming population across cosmic time. And yeah, I will end on a few perspectives on what work awaits us still to be able to really harness this emission mechanism to the fullest in the SKA era. So yeah, it is often stated, and I'm sure you've heard this statement made many times, that radio emission, by virtue of its long wavelength, is a dust-free tracer. And this is just another way of showing this, okay, which you may not have seen as frequently as other representations. So in the background, you have a face-on galaxy on the left, a low redshift disk galaxy, and an edge-on disk galaxy on the right. And yeah, my collaborator, Sarah Leslie et al. With some of our colleagues a few years ago, we looked at basically the variation in the intrinsic properties inferred for face-on and edge-on galaxies. So the plot here on the left has a sort of average star formation rate level measured in the ultraviolet on the left. That's at the left-hand side of this sloping line. And on the right, for edge-on galaxies, you see that this characteristic star formation rate is reduced compared to the face-on configuration. So what we find uniformly, pretty much for galaxies throughout the last 6-7 gigayears, is that the UV attenuation for face-on galaxies is roughly 4 times reduced compared to edge-on galaxies. And you can see this very well, of course, in the background, that dark dust band for the edge-on galaxy. But now, you know, you use radio emission, and this trend, the dashed line here, that's all you should look at if you squint, right? The 2 examples, it's sloped here, but no gradient for the radio emission. So this really just exemplifies this dust-free nature of radio emission as a star formation rate tracer on the example of galaxy orientation. But of course, yeah, this different mix of dust-obscured star formation activity and dust-free or transparent star formation activity occurs in different ways throughout much of cosmic history. So these are a few examples. Lower left corner, you see the cosmic star formation rate density, so the amount of star formation per unit co-moving volume on the y-axis as a function of look-back time on the x-axis. And you see the orange curve, the obscured star formation rate density dominates the unobscured component over a substantial fraction of cosmic time. And even at the very highest redshifts, it still has a role to play, as increasingly recent observations suggest. But it's not just a time effect, it's also differential at a given timestamp, so to speak. So looking at the upper right corner, you see this obscured fraction on the y-axis as a function of the stellar mass. And just following the black line here, fitted to the underlying colored data points, you see how this obscured fraction varies very substantially as a function of stellar mass, and it does so in a similar way for a broad range of redshifts. So yeah, clearly, you know, having a complete inventory of star formation activity would much benefit from a tracer like the radio emission, which is not biased by dust. And yeah, there are very pragmatic reasons for that. You just want to have good measurements, of course, bias-free measurements, but it's also important in understanding scaling relations and, you know, comparing to theory, to galaxy formation theory. So the lower left plot here is just a cartoon, basically showing, you know, for a scaling relation which is dear to many of us extragalactic astronomers, the so-called main sequence of star-forming galaxies, this gray band here, and a scenario for how galaxies with time evolve in the locus defined by this star-forming main sequence. You see here fluctuations basically within this gray band, potentially a departure at the end of the life of a galaxy. And so you can immediately see from this, right, that the degree of scatter this star-forming main sequence has, MS here stands for main sequence, can really give us insight on formation processes and evolutionary processes. And so the right-hand side is then just an example by Keshin Guo roughly 10 years ago, where she has measured in a differential way, and the color data points up here are just, you know, aligned along this gray band in analogy on the left. And the histograms on the right here basically show you systematically for different measurement approaches that red galaxies, and the red histograms here, have more scatter than at low masses, the blue galaxies. Okay, galaxies plotted in blue. So, right, this could be directly used potentially to constrain galaxy formation theory, but so far plots like these on the right have basically been constructed with a mixture of ultraviolet and infrared to trace star formation rate. So it would be a great advantage to have a single tracer rather than a hybrid one, where both components have their different biases and particularities. a single tracer would do it all in one go, and you'd have a consistent methodology across the entire mass range and star formation rate range. And yeah, this advantage of not being impacted by dust is also very impactful in a resolved view of galaxy formation. So often galaxy centers are where a lot of the action takes place. You know, the buildup of spheroid components over time, AGN activity, feedback, and the plot on the top right illustrates this for redshift 1 galaxies in a study by Morselli et al. And you see here, galaxy radius on the x-axis and a measure of extinction on the y-axis, especially for star-forming galaxies, which use the bluer profiles here. Extinction is really highest towards the center of galaxies. And so being able to penetrate that extinction is really important, and radio can offer that service to some extent. It does so, in an example on the left, for even the most dust-obscured nuclei in the local universe. And in the lower right corner, you see an example how, as you go from ultraviolet emission in the blue stamp for a redshift 1.3 Andromeda galaxy progenitor to increasingly longer wavelengths, you see how the star formation activity gets more and more centrally concentrated. So again, highlighting that lots of the action takes place in dust-obscured regions. So yeah, being dust-free, a huge advantage, but it's not only that, especially in interferometric imaging, of course, high angular resolution is reached, and this is essential as well. And this is a very busy slide where I don't at all want you to look at the details, but of course, if you have a high angular resolution, this really helps you separate out individual galaxies in dense regions, for instance, where you might otherwise blend them and generate or have to contend with source confusion. And just how serious an issue this is exemplified by the 3 columns here, where basically 3 different studies using different tracers, using different methodologies, when it comes to measuring the properties of this galaxy main sequence as a function of redshift and environment, come to 3 different conclusions, going from variation across all redshifts, a strong environmental dependence of this galaxy main sequence, to no environmental dependence. So clearly there are strong open questions here that need resolving, and a high resolution tracer like the radio can help address this. And fundamentally, this goes back to the very early days of pinpointing submillimeter galaxies with the help of high angular resolution interferometric radio maps. And yeah, that's an example here by Ivison et al. Around the turn of the millennium, just showing in the central column, it's most easily viewed. Maybe the lower row, you have contours here in the superimposed on the K-band map, which is the scuba detection, but multiple contenders for being the source of this emission, these 2 bright dots here, and the radio emission then helping you to locate which is the actual emitting source and helping us to quantify the spectral properties of these high redshift dusty starbursts across the electromagnetic spectrum. So very briefly, most of my talk will be on monochromatic work in radio bands to characterize cosmic star formation processes. But of course, there is a distinct advantage in having multi-frequency observations. And this is really an area of future development, especially into the SKA era, although a lot of work will still be done with single bands. But these are a couple of examples, basically allowing you to study with more refinement the properties of star-forming galaxies, and also the star formation history and timescales for star formation. So on the left-hand side, for instance, is an example where with the dotted lines, the authors, Thompson et al., have connected data points for an average spectral energy distribution of a redshift 3 starburst galaxy. And if you see even mild breaks, so not perfectly straight synchrotron slopes, the presence of such breaks allows you to infer information about the age of the star formation episode. And yeah, what this study here has concluded that is that at those redshifts, the sample which shows these breaks in the spectrum, their star formation kicked off roughly 40 to 50 million years ago. So quite consistent with the general ages of starburst events throughout cosmic time, but inferred through the radio. And yeah, for epoch of reionization, analog galaxies at low redshift, I just want to highlight this result in the middle from Omkar Bait and collaborators, where the Lyman continuum escape fraction is found to be highest for flat spectrum sources, so in the upper right corner here. And yeah, this work on epoch of reionization analog galaxies at low redshift, then for post-starburst galaxies with longer ages, larger ages, and steeper spectra, they found the smallest escape fraction. So again, highlighting the diagnostic power potentially of radiospectral properties to infer something also about other physical properties of such starburst galaxies. Okay, so I did briefly want to speak about challenges as well. And star-forming galaxies are often quite faint in the radio. We are not talking about very bright radio outflows with characteristic radio AGN lobes, FR1s or FR2s. So the regime in which the radio sky is really dominated by the emission from star-forming galaxies is highlighted by these figures here, both showing the same, different sides of the same story. So looking at the study from Matthews et al. On the left using Meerkat data, you see the blue curve here on the left-hand, in the left-hand half of the figure. It is the number counts contribution from star-forming galaxies, and you can see it dominates the red curve, which is the contribution from AGN at basically sub-millijansky levels, and clear dominance is only established sort of here in the several tens of microjansky or microjansky regime. This is a fairly simplified view of the galaxy population, splitting in a very binary way into star-forming galaxies and AGN. But yeah, the community is building, and the right-hand plot is an example of this, much more refined models, which really looks at the microjansky population in much more detail as well, and has additional contributions from radio quiet or radio silent AGN. And one of the challenges really is, if you want to use radio continuum emission to do an accounting of the star formation activity in galaxies throughout cosmic time, the challenge is the ability to be able to decompose between AGN contribution and star formation contribution in galaxies. And this often, these processes can occur contemporaneously. So yeah, just an example here on the left, and I'll leave it at that, a statistical study using stacking of radio maps for galaxies with different masses and up to cosmic noon. You see here on the y-axis, the relative ratio of the 1.4 gigahertz luminosity coming from AGN in the numerator and coming from star formation in the denominator. And the dashed line is simply a linear ratio of 1. So you see that the relative importance of AGN emission to the overall radio emission for galaxies on the main sequence, for instance, and this is the population studied here, it varies very strongly with stellar mass. Okay, so yeah, this is important to take into account when you want to do a detailed accounting of the star formation activity in galaxies across cosmic time. So yeah, a lot of work has been done. Being cognizant of all these challenges in the last several decades. And I just want to show you a few of the most recent incarnations of, basically measurements of the cosmic star formation activity using the radio band. So this study by Leslie et al. 2020 in the Cosmos field really tracked 4 galaxies of different stellar masses. And you see this with the different colors here as a function of redshift, the level of activity, the specific star formation rate. So star formation rate divided by stellar mass as a function of time. And you see this evolution, which is found also at other wavelengths. And this is just the proof, right? The evolution towards higher star formation rates at higher redshifts, and a slowing down of that evolution specifically as well, as you see here at the highest redshifts. And the interesting thing which one can do if you really have large samples of galaxies in the radio, and you know that the dust-free, dust-unbiased tracer can work for different types of galaxies, you can look at this in a differential way for different types of disk galaxies, for instance. So just looking at the plots on the diagonal here, the information is very much the same as on the left. We're looking at the star formation rate stellar mass correlation, and disky late type galaxies, you see here, have a very linear star formation rate stellar mass relation, whereas for bulge dominated late type galaxies, you see more evidence of curvature, reminiscent to the flattening which is going on, say, also for early type galaxies. So one can really understand mass buildup in different types of galaxies thanks to radio emission in this way. And of course, what all this evolution feeds into is the ultimate plot of the cosmic star formation rate density, which is the summary of all of this. And this is just to highlight, right, that with radio emission, whether it be the synchrotron continuum on the top, or increasingly also with larger area bars, but establishing overall consistency, using the free emission, the thermal emission, the radio data tracks the cosmic star formation rate density in a pretty consistent way compared to other tracers in multi-wavelength surveys, specifically finding the peak epoch to be around redshift 2. And yeah, the nice thing is one can look in a lot more detail, of course, which are the dominant contributors to this star formation rate density, and what are their properties. And this is an area where radio emission certainly can play its role. I'm showing here a plot from Karim et al. Using the original VLA Cosmos data at 1.4 gigahertz, roughly 15 years ago. And what you can see here is that if you look at these different curves, this is the relative contribution of galaxies with different stellar mass and redshift, the redshift being the different colors, to the cosmic star formation rate density. So going back here, right, you have this overall volumetric star formation rate going on in the universe, but of course the different mass scales of galaxies don't all contribute in similar ways. So what Alex Karim was able to show was that it's really the Milky Way galaxies with masses of a few 10 to the 10 solar masses that contribute in a dominant way at all redshifts. And this calls into mind also the sweet spot in terms of dominance from star formation feedback or AGN feedback, and the ability at roughly these mass scales really to incorporate baryons most effectively inside the dark matter halo into the galactic disks and stellar component. And this was a result which in a similar way had been found just a year prior using nebular emission lines. So again, I'm showing you this to just highlight the consistency of what is found with radio emission and other tracers. And yeah, with high resolution radio data, of course, you can then also start to measure the distribution of star formation rate, the characteristic scales of star formation rate within galaxies. So the left-hand plot is a recent work by Eric Jimenez Andrade, where on the x-axis, as a function of stellar mass, size measures are plotted for star-forming galaxies, in this case around redshift 1. And you see that the radio effective radii, the characteristic radii, are somewhat lower than the UV or optically measured effective radii of star-forming galaxies. Again, you're potentially recalling this ability of the radio emission to penetrate more deeply into the dust-obscured centers of galaxies, and revealing a more concentrated star formation distribution than one might otherwise have been able to detect. There are other measurement-related systematics which might be at play here as well, but for sure what one can say, using always radio emission as a tracer, and this is the figure in the lower right corner, regardless of what relative systematics there might be between optical and radio, if you use radio, you can detect that for the most intense starbursts, off main sequence galaxies, and I hope you can see my cursor circling the relevant data points. So in these panels, going from the left to right, from the main sequence here, the leftmost data point to the right, that is a starburst which is well above the main sequence, the size systematically decreases towards the most intense starbursts. And yeah, this is really where radio emission excels. Usually these dust obscured starbursts would be characterized with infrared emission, but infrared point spread functions are usually very broad, so it's really hard to access this information, this size information, in a consistent way for more extended star formation events and for the most compact ones. So I see my time is almost up, which is why I just want to leave you with a few final, more philosophical thoughts in some sense. I've argued that we have learned a lot about the star-forming population already, about the interplay between AGN activity and star formation activity by using deep extragalactic radio continuum surveys. But we do also, especially as we expand to lower luminosities, to larger areas where we have where we can achieve a better sampling of the rarer, brighter objects, we do have challenges to address as well. And a lot has really to do with the ability to, in an accurate way, measure star formation rates for star-forming galaxies using the radio band. The plot on the left here shows you, and this is again taken from Sarah Leslie's work, different ways, different recipes for inferring star formation rate from a 1.4 gigahertz continuum luminosity. And you see a whole band here of colored lines with substantial vertical offset of up to 0.5 dec. So maybe of order a factor of 3 here at the core, which is the best constrained regions through data. But of course, these relationships diverge to a substantial extent towards lower luminosities or higher luminosities. And establishing all the different factors that influence the calibration of radio emission as a star formation rate tracer really is an area of work at the moment. And it, in many cases, boils down to sort of calibration coefficients in an equation as simple as the one highlighted in the red box here. So star formation rate being proportional to 1.4 gigahertz or another radio continuum luminosity, and a calibration factor which we need to measure. So does that calibration depend on redshift? Does it depend on stellar mass, on radioluminosity in a nonlinear case? Does it depend on galaxy type? These questions are at the center of a lot of the work we are doing at the moment to take it to the next step. And so in closing, and as I know that many of you are interested in the star-forming galaxy population just as a foreground emission signal, I did want to end on the message that we have learned a lot and that the radio view of the star-forming galaxy population is well developed, certainly in statistical terms. So the final slide I'm showing here contains a plot from a very recent paper by Giulietti et al., where you see in black model curves for the luminosity function, the 1.4 gigahertz luminosity function of star-forming galaxies in the radio band, going from low redshift all the way up to redshift 6. And you see that these black curves manage to reproduce the data in a very satisfactory way overall. And the way these model curves have been derived is starting with the stellar mass distribution of star-forming galaxies and convolving the stellar mass distribution with scaling relations, okay? So taking one known statistical distribution, convolving it with correlations the galaxy population follows, and predicting the radio properties of that population. And as you can see here, that exercise works well. And it really provides a solid basis for survey planning or also population modeling. So for instance, for EOR or cosmological EOR foreground or cosmological probe populations. So in summary, and I'll end here, the key advantages of galaxy evolution science using radio continuum surveys are the high sensitivity you can reach, especially with the next generation of radio telescopes, the confusion-free nature, and the dust unbiased nature. And of course, there's a very appealing aspect that you can derive continuum maps from what was originally a radio cube. So H1 in many cases can be done at the same time. There are known challenges. I've alluded to these: AGN star formation separation, the faintness of the targets, and of course also ancillary data is really important for this due to the nearly featureless nature of the radio spectral energy distribution. I've given you a bit of a taste for what all we have learned about the star-forming galaxy population, so I'll leave it at that. And yeah, just to say that we are still working hard to make the most of this mechanism for tracing star formation activity. Thank you.
Question for Mark?
Yeah, hi Mark, nice talk. So this last slide, the one before, regarding this radioluminosity function, evolution as a function of redshift. You have plotted against the T-Rex, the models which we use typically to populate our foreground sky in simulations.
Yes.
And we saw that there is at the lower radio power, the curve actually digresses from the results a lot. Yeah. So if you look at redshift beyond 2 or from 1.6 onward, I think, at the lower end, below 23 of log luminosity, I think the T-Rex curve deviates from your mean curve, I think, a lot. Why this is?
Yeah, I mean, basically, but below the knee of the luminosity function, right, one could say, there start to be substantial discrepancies.
What would be the potential reason?
And even at high luminosities, you see this especially at the higher redshifts. So this depends a lot on processes that happen in low mass galaxies. You know, low radioluminosities translate in a somewhat direct way to low stellar masses. So what happens here, for instance, is that you need to take into account the balance between dust unobscured and dust obscured emission, which changes across the different mass scales. So that could be a reason. Another reason could be, you know, the separation that is being done between star formation and AGN. I don't know how clearly this can be done. You see here the T-Rex curve is for star-forming galaxies and radio quiet, right? So you already have a sum of two populations here. It's not necessarily exactly the same sum in the empirical modeling. So yeah, this would need a close look. But yeah, I can think of a few reasons why this would happen. And of course, I mean, bear in mind, right, even the low mass slope, the original stellar mass distribution that underpins all of this comes with a certain uncertainty. So the very starting point for the black curves at low stellar masses has a certain error. So if one were to plot the black curve with a full-fledged uncertainty, you might find that there is some overlap, potentially, within 2 sigma or so with the T-Rex curves. But yeah, that would have to be fleshed out in more detail, and this is something these authors certainly could do.
We are running a little bit late, so I will request you, if you have questions, then put those on Slack. Let's thank the speaker again.